might as well start. That time was completely off, but anyway, sorry. We left off last time talking, giving a very, very brief introduction to graphs, or not a brief introduction, but a review. That you've got these vertices, you've got edges connecting the vertices. You could have directed graphs. You could have. We generally will deal with undirected graphs. Sometimes we'll deal with weighted graphs, where you've got weights on each of the edges, right? And then we talked about various ways of representing those graphs, like adjacency matrices, adjacency lists, maps, sets, like sets of tuples, et cetera, et cetera. What I'm going to recommend, especially since everybody is using Python, is to simply use NetworkX. Has anybody used NetworkX before, Python? No? Okay. So I've got a tutorial here ready to go. I mean, there's a tutorial on its website here. But what I thought we would do is go ahead and play around with it a little bit and just walk you through the basics. So by default, the default type of graph is going to be an undirected graph. Just a second, let me make sure that the audio is going. Yep, good. All right, so the default type of graph is just going to be an undirected graph. And to create a new graph, well, you have to import NetworkX. And here I've aliased it to NX. That's what all of the tutorials do. NX.graph, right? And at this point, lowercase g is now a graph, okay? We can add nodes if we want, g.addNode. Right? You can add nodes with integer designations. You can add nodes with string designations if you want, right? So, or hello, and g.addNode, I don't know, 0, et cetera, et cetera. Now, in your assignments, all the nodes will be associated with the integers 0 through n-1, because that's good enough, right? And also, if you are going to roll your own graph representation with an adjacency matrix or list, then indexing them on 0 is going to be convenient, okay? You can also add multiple nodes at the same time, g.addNodes from, and then you can provide it a list. So, for example, 5, 6, 7, and 8, or whatever. There we go. That creates a graph with vertices. Now, how do you start connecting those vertices together? Well, actually, before we do that, let's go ahead and make sure that this works. And you can iterate over the vertices in a graph simply by asking for all the nodes. For node x in the graph g.nodes, right? G.node, as with everything with Python, if it's a class, there is no private class. There's only private conventions. So you do have access directly to the nodes themselves. And if you print each one of these out, then let's go ahead and Python 3 demo. There we go. You'll see that all those nodes are present in the graph. 0, hello, 5, 6, 7, and 8. Right? That's how you can iterate over nodes in a graph. You can find out the number of nodes if you want to, using the number of nodes. Right? And you can also find out the number of edges in the graph. M.number of edges. Right? There we go. How many edges do I have right now? Have I drawn any edges? Nope. So the number of edges is 0. Let's go ahead and add some edges here. To add an edge, what you have to do is, oh no. Sorry, I had it. There we go. You have to specify the beginning point and the end point, and then they're the same, right? So for example, you can go g.addEdge. I'm going to go ahead and add an edge from 5 to 7. That is exactly the same thing as adding an edge 7 to 5. And adding it twice will have no effect because this is an undirected graph. It's an undirected simple graph. You can have graphs where you've got two vertices and then multiple edges connecting them over and over again, even with undirected graphs. Those are called multi-graphs. You can have graphs where an edge goes from one vertex to itself. That's called a pseudo-graph. I don't think that this actually supports either one of those things, but let's go ahead and find out. Let's go ahead and add these edges and then ask how many edges there are. Because that first one is a pseudo edge, a self loop, that shouldn't have any effect. 7 to 5, 5 to 7, those are the same edge, so we really should only have one edge here. And, oh, unfortunately we have two. I don't know why. Yeah, go ahead.
Is it because when it makes a graph, it assumes it's like a directed graph?
Well, to get an undirected graph, you would have to call, I think, UNDIR graph, whatever the tutorial. If you go to that tutorial, you can see how to do it with a directed graph. This is, by default, this graph is undirected, though.
Oh, okay.
So I'm curious, did it allow that dual edge, or did it allow the self loop, basically? So let's find out. Let's go ahead and find out what are the edges. Actually, let's iterate over the edges. Iterate over the edges. Yeah, go ahead.
I'm sorry, I'm a little late. Can
Uh-huh.
you just summary what we're doing?
All right, sir. Sure. So let's see. This is NetworkX, right? We're bringing this in so that we don't have to roll our own graph library, right? We don't have to write an adjacency matrix or an adjacency list or anything like that. NetworkX, you can create a brand new graph here. You can add nodes either individually, or you can add nodes from an entire list. Right? You can mix nodes, so nodes can be associated with a string, an integer, or even I believe a floating point number. You can iterate over all the nodes that are in there, right? And here we've printed them out. You can find out how many nodes there are, how many edges there are, and here you can add edges. You just need a beginning vertex and an ending vertex. And then we can iterate over the edges to find out what those actually were. Print E. Right? So let's find out what edges are actually in this graph. So 5, 5, it did allow that self loop. That's quite surprising to me because that's a pseudo graph, right? So apparently it does support that, but certainly let's not do that because then a lot of the graph algorithms will get confused, right? You might get stuck in an infinite loop. I need to go to all my neighbors. I am a neighbor of myself, okay? Keep going over and over and over again. You can have that if you want to. You just need to make sure that you don't get caught in that kind of an infinite loop. That's how you can iterate over the edges, but an even better syntax for doing that, what is an edge? Conceptually, what is an edge? It's connecting one vertex to another vertex. It's a what? It's a tuple, exactly. So instead of calling this E, let's go ahead and unpack it into its vertices already, right? And so I will put in X connects or is adjacent to, and then Y. There we go. And you can see that 5 is adjacent to 7. Whether or not it goes in lexicographic order, I have no idea. Certainly, you should not be able. You should not make any assumptions about that. If you need to visit all the neighbor vertices in some particular order, like for your assignment coming up in a couple of weeks, then you will need to put some sort of a sorting or comparison-based order on that neighborhood. Okay. Let's see. Can iterate over the edges. Oh, and then attributes. You can attach attributes to either vertices or edges. Attributes here would be something other than the vertex name. The vertex name is just for the topology of the graph. If you actually want to put, say, a weight, or later on we'll be looking at colors of vertices so that we can keep track of them as breadcrumbs when we traverse through a graph. You can go ahead. You can easily. Let me go ahead and get a new graph here. No, I'll go ahead and go with this. Let's see. Set node attributes. There we go. I'll bring this over here. Right. So by default here, let me go ahead and get these colors. I forget what this does, but I don't think I need this actually. Yeah, you can do it like this, or you can do it manually. So let me go ahead and put that in a comment first of all. And let's go ahead and iterate over every vertex and set a color or something to it. For every vertex in G.nodes, right, we'll go ahead and set an attribute called color to it. G.nodes of X, right? That's how you can index that particular node. Now you've got that node object. And now what you can do is you can give it an attribute. So say color, right? And equal to blue. Right? Then we can iterate over it again if you want to after we're all done. And we can see that they're all, in fact, blue. So print X has color. And then I'll access it instead of setting it. G.nodes of X. And then its key value color here. I think that this will work. Yep, there we go. So you can change that. You can update it accordingly. Right? If you want to, there are ways. This is what I was working on before, and I decided to skip. But what you can do is you can set all of the nodes, all of their attributes all at once by using this set node attributes. Right? I'll go ahead and leave that as outside. Okay.
Would you be able to set their attributes, like, would that set all of their attributes with different color, or would that?
I forget, since I've only got 3 colors here, red, green, and blue. Whether or not if you provide a list whose length matches, I'm sure that it will do it in some sort of order. You'd have to RTM, read the documentation.
Okay.
Right? I forget. You can also do it with edges. So for X and Y in G.edges. And note here, I think it is an actual full-fledged function because it gives you a probably an iterable rather than nodes, which is just a list, right? The edge set is something a little bit more substantial in NetworkX, at least, right? It looks like to me. We can set the attribute of a particular edge. So a particular edge in G goes from X to Y, and then you can set the third attribute here of, say, a weight. And this is how you can get a weighted graph. I don't know, 10. There we go. And then you can print all those out as well. Here. So X in there, print X to Y has weight, and then whatever this happened to be, whatever it was set to before. There. Is that all good?
No,
There, that's better. All right, let's test that out. Yep, there's only one edge, so let's go ahead and put in some more edges here. What did the graph look like? There. So let's go with 6 to 8. Let's go with hello to 8. All right. Give me one more so it just is interesting.
7 to 0.
I want to keep 0 isolated though,
Oh, okay. Sure.
just to show you. 6 to 8. Oh, I already did that. 7 to 8. All right, there, that's good enough. Okay. And printed it out, and you can see that everything has a color of blue. Everything has a weight of 10. Right? Now, as bonus here, what I did, I think that I did this a couple of years ago, and then I just resurrected it just now. There's this other plugin kind of thing that is available in the standard Python 3 library. It's called NetworkXTXC or NetworkXTXC. TXC is it's a graphical library in LaTeX that allows you to. How many people have been using LaTeX? Like maybe like half of you, I think, have been. All right. Anyway, it's a nice way. You can install it with pip, just as you might have installed NetworkX with pip. You'd also have to install this other package, SciPy. It's scientific Python or whatever. But once you've done that, then what you can, and of course you would also have to have an instance of LaTeX that compiles LaTeX code into a PDF. But what you can do is you can define a style. Right? So the node label is going to be all these nodes, whatever the nodes are. A curved edge, I forget what that is, but this is just a little sample of what's possible. There are hundreds of different things that you can put into the style. But once you've got that, you can plot your graph using these styles. And when I do that, it's going to take a little bit longer than usual. Oh, it didn't. Okay, fine. I can PDF LaTeX it. What was it? mygraph.tech. It's now compiled, and I can come over here and, oh, where's my, fine. Let's see this. I need to open it up. Shared notes, fall, and here is the PDF associated with that graph. All right. That's kind of ugly, but whatever. All right.
How much do you space them out a little
Yeah, I'm sure that there's like spacing here. We'd have to look it up, but you can go. This is how you can say if you've got a really large graph and you want to verify your DFS or your BFS or whatever algorithm works on it, you can go ahead and dump it to a PDF file, and then take a look at it manually, basically. Right? Is the test case that you designed, is it correct? Well, look at it visually and then go back and forth with it. Right? Or you could just draw stuff by hand. But that is NetworkX, basically, to TXC, and there's a plotting tool within that library. There's a dependency on SciPy, but once you've got that, then it looks something like this. And there are the weights in between all of them. Again, the spacing is completely off here. I don't know, we have enough time. Network to TXC. Vertex spacing or distance, maybe. Distance, note label distance, edge label distance, force positions. Nope. Margins. So spacing, maybe. Nope. I don't know what it's going to be. So, but you can see there are hundreds, thousands of different options that you can use, and it'll end up drawing stuff like this. But then, of course, you do have to, have a LaTeX instance. But you shouldn't need to edit the LaTeX at all, right? In fact, if you want to take a look at what the LaTeX looks like, I can open that up as well. Well,
Just be in the notes for today.
I can commit it if you want, but let's see, shared notes. Here is the actual LaTeX code that it generates. I didn't write any of this. This was all just generated, and you can see that there's a vertex, there's edges. It produces a TXC picture. This is a standalone document, so if you want to, you can bring it. If you are using LaTeX, you can bring this standalone document in. You don't have to cut and paste stuff, basically. You can just include it as an external document and then keep it separate, because it's a standalone document. All right? So if you're wanting to take a look at what your graphs actually look like, you want a graphical user tool, this is the best one, at least as of 2 years that I found, and that's probably just my opinion because I know TXC and I use it a lot. All right. So there is your crash introduction to NetworkX. Any questions? All right. So I would recommend that you use it for your assignment, the next 2 assignments actually, because it's all programming and it's all graph algorithm stuff. But otherwise, we should start talking about some actual algorithms that you would need to actually implement. Yeah.
Would we be required to hand in any like LaTeX something?
Nope.
Okay.
Nope. Like you might have been required to use LaTeX for say 235H or not?
Yeah.
Yeah. Okay. So
Like
you can.
1%,
Right. All right. So our first algorithm is going to be a basic search algorithm, depth first search, which actually you already know. We covered depth first search, we just didn't call it depth first search in computer science 2 on a particular type of graph. If you have a tree, what are some tree traversal algorithms? Pre-order, post-order, and in-order. Those three, they're all depth first search algorithms. They go as deep into the tree to the left as possible before backtracking and then exploring another branch of the tree. Then backtracking and going as deep as possible. You go all the way down to a leaf until you reach a dead end, and then you backtrack and explore the rest of the graph. Those are all depth first search algorithms. It's just that the difference between those three was the order in which you enumerated the root node. Did you do it first, second, or third? Right? With depth first search, that's not just a tree, it's any graph. Right? And in fact, you've been exposed to this algorithm a second time. On your first assignment, when you did, what was it, Hamiltonian path? We did Hamiltonian path, right? Right. So Hamiltonian path, you were doing a depth first search. It's just that you were doing a really inefficient, exhaustive depth first search where you were searching for a particular type of path, a Hamiltonian path. Here with the depth first search, we want this to be efficient. The goal here is completely different. You're not looking for a Hamiltonian path. You are looking to explore the entire graph. You only want to look at each node once because you're searching for a particular node or you're searching for a particular property of a node or whatever, right? Depth first search is just a generic algorithm that allows you to start at a particular vertex, go through and explore the graph in an efficient manner so that you're only visiting each node at most once, okay? Or processing each node at most once. But you go as deep as possible before you start backtracking. We want to make sure we make progress. Right? We don't want to enumerate every possible path, or we don't want to repeat ourselves, repeat a node or path too much, that is. Right? We might repeat it at most once or twice or something like that for each vertex, etc. Our goal is to simply explore the graph and enumerate every vertex. And you can imagine that you're doing a depth first search. Of course, if you were searching for a particular node, you would stop once you found that node. Right? Or if you were searching for a particular node containing a particular piece of data, then you would do a depth first search until you find that piece of data and then you'd stop. That's the basic version of this algorithm. We will use depth first search as a basis for doing more complex things. For example, ST connectivity. Given these two vertices in a graph, are they connected? If so, how short of a path can you do? How long of a path can you do? That takes us all the way back to the first assignment and Hamiltonian path. Given a graph, does there exist a cycle in that graph? Right? A lot of other connectivity questions, a lot of other topology questions can be answered by using depth first search as a basis and then modifying it to get the property that you want. Right? And again, you've seen it before. Tree traversals are DFS. Right? Pre-order, in order, post order. And again, the strategy, we go as deep into the graph as possible before backtracking. Right? And along the way, we keep track of vital information. Right? So depth first search is kind of like maze exploration or getting lost in a forest. You want to make sure that you can make your way back, just like Hansel and Gretel. Hansel and Gretel, how did they find their way back? Breadcrumbs, right? So we are going to keep track of vital information known as breadcrumbs to know where we are, where we've been, and ultimately where we're going. We need to answer questions like, have you visited this vertex before? Right? Have you processed this vertex before? Right? When did you see the vertex? First see the vertex. When did you process the vertex, right? Et cetera, et cetera. When did you last see it? And so we're going to keep track of this information. And programmatically, of course, you can keep track of it in many different ways. But conceptually, what we're going to do is we're going to keep track of it through colors and timestamps. Okay. To do that, let's just go ahead and start with an example. Come on, just a second. Oh, you know what? I never started QuickTime. Sorry. I knew I was forgetting something. There we go. Okay. All right. I think that this is all on the screen. There we go. All right. So here's our first graph. It's a reasonably sized graph here. With a depth-first search, there are lots of ways that you can go about it. You can start at an arbitrary vertex, or you can start at the lexicographic least vertex. When I'm at a vertex, I need to make a decision. Where do I go next? I look at the neighborhood, the things that are immediately connected to it, and I need to make a decision that I go to that vertex next, or that vertex next. Without loss of generality, we'll just go ahead and say that it's lexicographic. Okay. Yep, there we go. All right, so let's go ahead and do a lexicographic then. We'll go ahead and start at A. Right. We're also going to keep track of a couple of things. We're going to keep track of discovery time. In other words, as I progress through this algorithm, the first time that I visit a vertex, I'm going to say, timestamp it. I've discovered this vertex at timestamp 1. And we'll just keep a simple counter. 2, 3, 4, 5. We'll also keep track of finish time. This is a time when we process it and we never want to see this thing again because we're done with it. Okay? Remember that we go as deep as possible until we hit a dead end. And then that's when we start to process the node and then start backtracking. Okay? We're also going to keep track of colors. A white vertex will indicate that it is unvisited. Right? We haven't seen it yet. Initially, before the algorithm starts, all the vertices are white. Right? We will then keep track of a gray vertex. AY is the American spelling, or not? EY? AY? Okay, all right. We'll be Brits or English or Americans. I don't know which one. Visited, but not processed. In other words, the first time we see it, we say, okay, great. I've discovered this thing. Color it gray because it's no longer undiscovered. And then move on because I'm going to come back to it eventually and process it. Okay? And then finally, black. Visited, or now this is the end. It's been processed. Okay? Now those three colors are chosen to be white, gray, and black because in textbooks, printing, of course, it's much cheaper to print in grayscale. If you want to, since I've got highlighters here, we can go ahead and go with, these nice pretty colors or whatever. If you were actually programming this, does it matter what colors you use? No, in fact, I would use English language descriptions. Visited, unvisited, processed, right? Instead of colors, because I would lose my memory of what those colors represent pretty quickly, right? Okay, so let's go ahead and start with the DFS here, and I will demonstrate what I mean by this. Graphically, that is, right? So I'm going to start at A. Well, I've started out this counter system, right? And I discovered it at 1. And I'm going to also color it. Oops, nope, that's my eraser. I'll color it whatever this color is here, magenta, right? So that's going to be my gray. All right. Simply because if I start coloring things black, then I will lose the labels and I won't remember what they are. Okay? All right. So, what is my next step here? I'm going to look at the neighborhood of this thing. I could go over to I could go over to C, I could go over to B, I could go over to H. Right? I've got a lot of choices here. And this is white, 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 white. All of them are unvisited. If I had something that was already visited or processed, should I go to it a second time? No. That takes you back to the first week where you were searching for a Hamiltonian path and you end up with an exponential time algorithm. We only want to visit things at most once. We only want to process them at most once, I should say. Okay? So what order do we want to go in? Well, let's go ahead and go in lexicographic order. Okay? That means that I'm going to go over to B next. I am going to keep track of where I'm going here by keeping track of this red line. I went from A to B because that's what the next lexicographically unvisited vertex was in its neighborhood. That's been visited, and I label it as 2 because this is a time counter. It's always incrementing. 1, 2, 3, 4. Whatever I'm doing at that moment, I take that counter and I stamp it with that counter. And I discovered it at timestamp 2. This leaves a breadcrumb trail, right? You discovered A, then you discovered B, then you discovered, right? And you'll be able to retrace your DFS path that you built along the way by labeling these things, right? All right, once again, I am at this vertex, but the neighborhood, looking at it, it's connected to A, C, D, and G. Well, lexicographically, A is the least one. Should I backtrack and go back to A? No, why? It's been colored gray magenta. You don't visit things twice, except when you're pulling back and when you're backtracking, okay? So, let's go to C, right? Because that's the lexicographically next one. At C, I look at its neighborhood, and I'm connected to A and B, but those have already been visited. So my only candidate here is D. So let's go ahead and go to D, 4. And sorry, I should be updating the path that I took. There. And then color D gray because you just visited it. At D, I look at its neighborhood. And once again, I see C and B here, but they're already been visited. By the way, looking back at B now, right? Looking back at C doesn't tell me anything because that's where I came from, right? But looking from D to B, what does that tell me? I'm at a current vertex here, and I'm connected to a gray vertex, gray magenta vertex, that I did not immediately come from. There's a special type of path called a, well, it's a triangle set, yes, but in general in graphs we call these things what? Cycles, right? Cycle detection. DFS can be used to detect cycles like this, right? All right, next. I see G, E, and F as unvisited vertices, so I'll go ahead and go over here to E, right? Keeping track of where you came from, and there. Next iteration, I will go over to F, because that's my only choice, right? I could go to D, but it's already been colored gray, magenta. I've visited it, so 6. Where am I going to go next? I, 7. And let me go ahead and update everything up to that point. And my highlighter here. Because now something new is about to happen. When you're at I, and you look at the neighborhood, are there any unvisited vertices in your neighborhood? Nope. At which point I start backtracking. I has to be processed though, because I've reached a dead end. I process I, and I timestamp it with a finishing timestamp. 8. Right, I'm just using the same counter for both of these. Right? And I'll use a different color here, gray. There. That's almost black, right? Yeah.
Did you keep track of like these timestamps for the nodes when they're visited or when they're processed? Would you keep track of that in the nodes or in the graph? graph or the function.
Yeah, I just showed you how to do that, didn't I? There's a color. You could also have status. You could also have discovery time stamp. You could have finish time stamp. You could have whatever you want, because this is just a key. This is just a string.
Alright, yeah, that makes sense. I was just wondering
Yep.
where to put that data.
Anywhere you want. You could even store it outside the node if you want to.
Well,
You
I
could
thought-
store it in a map of attributes or something.
Yeah.
All right, so I backtrack, and now I'm back over here. I look at the neighborhood, and now I see a different neighborhood. I see a black vertex. I see a two magenta vertices here, but I have nowhere else to go. So I continue with this backtracking. 9, and F is now done. Okay. I continue this backtracking all the way until when? 10. And now I'm at D, right? I look at D's neighborhood. I see 2 black vertices that have already been processed. I see 2 gray vertices that still need to be processed, but I don't want to visit them a second time. And so where do I go next? G. And it has a discovery time of 11. And then highlight it, magenta, and keep track of where you came from. Okay. There's only one choice left at this point. I go from G over to H with a discovery time of 12. And I highlight it. And now at this point, I've discovered everything. And so I just have one big giant backtrack. Right? The backtracking is going to end up being 13. And now it's black. Right? Backtrack to 14. Color it black. 14, 15, 16, 17, and 18. And at the end, they are all, oops, well, I suppose I could do that, but I want to keep the highlight here. At the end, they all get colored black, and we're done. I enumerated everything. I processed everything. And I have some artifacts here that help me with reconstructing the path that I took. I went here, 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 here. I backtracked and then explored over that way. In fact, what you can do is you can take that and produce something else, another artifact called a DFS tree. So a DFS tree. Let's go ahead and, what was it? A, B, C, D, E, F. So it was A, B, C, D, E, F. And then where did I go? I went from F to I. So I was next. That's kind of ugly I. There we go. There we go. And then I backtracked all the way to D, and then hanging off of that should be G and H. G and H. There's my DFS tree. If I draw it top to bottom, right, then it forms a tree. I've taken out all of those other edges, right? So let's put those other edges back in, but with a different color. One such edge is A to I and A to C. A to I and A to C. Right? In the original graph, we also had what? DB and DF. So DB and DF. There we go. All right. And finally, there's 1, 2, 3, 4. A to H and A and BG. So BG. And there's also one AH. There we go. So the black ones are tree edges, right? So they're tree edges. The edges you traversed in the DFS algorithm. And then there are these other types of edges. Okay? You can categorize them in a couple of ways. You can call them forward edges, back edges, or what are called cross edges. Okay? Not all of these are going to be here. Forward edges are clear. If I started think of this as a tree because that's what it is. If I started an ancestor here, A, and I jump all the way down here to a descendant, I, that is a forward edge. Okay? I'm going from a shallow part of the tree to a deeper part of the tree. What about A to C? Well, that's from an ancestor to a descendant, so that's also a forward edge. Forward edge because D goes down to F. Forward edge, forward edge, forward edge. I don't see any back edges here. What would a back edge be? If this orientation is forward, then this orientation is backwards, right? So technically, this is also a back edge, but that's only because it's undirected, right? For undirected graphs, so forward edges, they connect a descendant, or actually an ancestor to descendant. For back edges, an undirected graph, same. But you can imagine if we did this on a directed graph instead, right? You could have a DFS tree here where this was going from an ancestor to a descendant, and then this one was going from a descendant up to an ancestor. All of these, of course, are oriented down. Otherwise, they wouldn't have been in the DFS to begin with, right? So for an undirected graph, these are the same. What a cross edge does is it does not connect an immediate ancestor to a descendant. It connects siblings or cousins or aunts and uncles, right? It connects, this is all other edges. Right? So one such edge that you can think about, let me draw it in blue here, is maybe E to G. If that's not blue enough. All right, there, that's blue. That's not blue enough either. All right, something completely different. Yellow. You can't even see that. Green. There we go. That's easier to see. All right.
Does that exist in the graph?
Well, it didn't exist in this particular graph. What I'm going to argue is it doesn't exist in any graph for an undirected graph. Now let's understand that first of all. First of all, understanding what a cross edge is. Is E an ancestor of G? Nope. Is G an ancestor or a descendant of E? Nope. So what if they were to be connected here? Right? Is this possible with the DFS traversal? What would have had to happen? We did our DFS by going A, B, C, D, E, F, G, I, right? And then we started backtracking. We backtracked. If this edge had been there, would G have been discovered yet? I would have gone from E to G instead, putting this into an ancestor descendant relationship. And this edge would have then become a forward edge. So for all other edges for DFS on undirected graphs, not possible. All right? But for directed graphs, it is possible. Why? Because of the orientation. Again, let's use the same reasoning that said that this wouldn't have happened. We would have gone from E to G. But what if it was oriented that way? Could we have gone from E to G? Nope. Because you can only traverse forward in an oriented edge. Okay? So all four of these are possible in an undirected graph, but for a directed graph, only tree edges and forward edges are possible. The presence of a forward edge tells you what? All these are tree edges, tree edges, tree edges, tree edges. The presence of a forward edge tells you what?
Shorter path.
There is a shorter path, certainly, but what is that thing? It's a cycle, right? So you can use this for cycle detection. If there are only tree edges, you're done. There's no cycle, because the DFS tree is a tree, which is an acyclic graph. If there are forward edges, then that means that there's must be some cycle somewhere. Yeah.
How do we detect edges that we've never like come across before? Or like that we never go across in the DFS tree? Or
Well, they're still part of the original graph. You've got one edge set and another edge set. If the difference between those edge sets is not the empty set, all the rest of them are going to be forward edges.
and we could just add those to the DFS tree if they have.
Well, if you're building a DFS tree, sure.
Will we need to?
Maybe, maybe not. I don't know.
Okay.
It's a fun little exercise to do so.
Uh,
Okay. So one other thing before we call it a break. What if I had the following graph? A to B to C, D, E, and F to G and H. There we go. There's a graph. It's not two graphs. This is a graph with two components. Just because these components are separated and there is no path between them doesn't mean that that can happen, right? You can even have, say, HI over here. You can even have an isolated vertex, a vertex of degree 0, right? How do I do DFS on this? Well, really quickly here, I would simulate it by going A to B to C to D to E, and then start backtracking. Am I done with my DFS? Did I explore the entire graph? I explored that component, but did I explore the entire graph? Nope. I need to start over, right? There are still white unvisited vertices. So restart the process at one of those white vertices. And again, you can go in lexicographic order. What's the next one? F. What's the next one? G. You backtrack. Right? Then you go over to H. You backtrack and backtrack. Am I done with the process yet? Nope. Visit. Backtrack. And now all of the vertices are black. That is the condition for stopping your DFS. Okay? So we don't have enough time to start going over pseudocode for it, but you can imagine one of two ways of doing this. If you remember, especially pre-order, post-order, and pre-order, in-order, and post-order traversal, the easy way is to simply use recursion, right? Where you explore the left child, then the right child, and then you process the node first between those two recursive calls, or last after those two recursive calls. You can abuse the stack space, the program stack, to do your work for you. What's an alternative? Create your own stack, right? And literally it's a stack, right? Push down a stack. And you keep track, and your stack then becomes your breadcrumbs. You start at A, then you go to B, then you go to C, then you go to D, right? And then you start backtracking, you start popping things off the top. You reverse your path. This stack is your breadcrumbs. There was the stack at one point. And then we started popping things off. Oops. We went back, popped, popped, popped. Here's my stack. Oh, come on. Here's my stack right now. Push, push. Pop, 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 pop. All the way back to the beginning, right? So by using just a regular old stack and keeping track of all this stuff, really, really simple, easy, straightforward algorithm. one quick note on the efficiency here. At most, how many times do I process a node?
No,
Process a node.
sorry.
Well,
I wasn't here for that.
Process a node.
One.
Once, right? I don't reprocess it. How many times do I visit a node in order to color it a different color or to see that it's already colored gray or black, so don't visit it? Now you're getting into the number of edges, right? Which one of those is my elementary operation? Visiting? Okay. You can look at it from either way. Either direction is not. Both of those are equally good, but think about what you're actually doing some data, right? And so ultimately, you're processing your data is probably going to be way more expensive than just traversing your data, right? And so ultimately, in my opinion at least, you should focus on how many times you end up processing something. And if you process something only exactly once, guess what? It's order n, where n is the number of nodes. Right? Now, if there's data on the edges, that's a different story, right? If it's data on the edges and you're processing every edge exactly once, now it's order m, where m is the number of edges that you have in your graph. And m can be bound from above and below. I don't have it in this set. I switch over so that the PDFs don't become too big on GitHub. But in the last one, we showed that there was a bound. M, the number of edges, is between 0 and n choose 2. N choose 2 is order n squared. So we have a bound. They're both polynomially related. That's why one answer is not better than the other answer. It's all just polynomial relationships. All right? All right, have a good break.
I have a question.
Yeah, go ahead.